The universe of today's presentation is described in three aspects: the key, the infinity symbol, and the QR code. The key is describing the security aspect of what we're discussing today. The infinity symbol stands for the life cycle of software, so it represents the software. And the QR code is representing the supply chain, because in many aspects of supply chain in the real world, not in the virtual and software world, QR codes help to testify a supply chain. So today we are discussing the secure software supply chain. My name is Matthias Eckermann. I'm head of product management Linux platforms at SUSE, 30 years working in the open source world, 25 years with Linux, and over 20 years with SUSE. We are approaching today's topic in 6 steps. First, we look at what a secure software supply chain is about. Second, we see what security aspects we need to consider. Third, we are discussing the software lifecycle and bring in all the security aspects discussed before into the software lifecycle. Then number 4, we look very briefly into example initiatives in the open source world. And then we look very specifically at the aspect of building, which is the weakest link in a secure software supply chain. And I will end with a small call to action for all of us. First, what is a secure software supply chain? Allow me to read the definition. A secure software supply chain is the ability to secure, document, and trace sources and binaries, build environment, and update mechanisms of a specific workload over its full life cycle. But why do we care about this? We do care because there is an increasing number of supply chain attacks that we have seen just recently. I don't think I need to mention all the separate names, starting with solars and winds and whatnot. Second point is that software is ubiquitous. Ubiquitous means that software applies to all areas of human life, not only to technology or finance where it was before, but it also approaches healthcare more and more. It goes into travel, up to self-driving cars. It takes decisions for us when we think about artificial intelligence. So that means that the security of the software and that its proven quality is a very important aspect and approaches more and more areas of our life. This means that the risk that a broken software supply chain goes far beyond the pure technology level that we are discussing here. In that context, a secure software supply chain is a matter of risk mitigation. Or, speaking from the other perspective, it is about trust and control. It is about trust and control into machines. It is about trust and control about processes. Also, subsequently, about businesses. It is a control on human beings. And it is trust and control on the data, on company data, but also on personal data when we think about data privacy, for example, where this plays a fundamental role. So we can expand the definition of a secure software supply chain. It is the ability to secure, document, and trace sources and binaries, build environments, and update mechanisms of a specific workload over its full lifecycle, to gain trust into and keep control over machines, processes, businesses, human beings, and finally, and most important, data. When we have defined this, let's now look into the details of the security aspects that need to be considered. And there are specific definitions that all of us should be aware when we are talking about security. First, there is confidentiality. This means that an information shall only be disclosed to authorized entities. The second aspect is integrity. Information is only modified by authorized entities. There is the aspect of availability. This means that the information is accessible in an appropriate time, so this means quickly. It also means that the information is accessible for an appropriate time. Let's think about a long life cycle where I may need information to confirm a secure software supply chain over a very long time. Authentication talks about the origin, the originality of the information. An aspect that is often forgotten and is not so easy to explain is non-repudiation. It means that the information is indisputable. This means I can tell that I am not the author of something specific, or someone else can prove that I am the author of a specific thing. And it overlaps a little bit with accountability, which means that the information can be associated to an origin, and also the opposite of this, to anonymity, that the information cannot be associated to an origin. The aspect of anonymity today, in our today's discussion, is not that important. But what is meant with information here? Information or assets of software, and for software, we can look into 6 categories. If we are looking at a software product, it is about the product configuration and the metadata of the product. It is definitely, though, also about the source code of the software, and it is about the binary code, very obviously. However, there is more information and assets associated, like, for example, security-related information. So this can be vulnerabilities, known and unknown, specific security configuration. Here it overlaps a little bit with the product configuration. But also, for someone offering software, customer-related information is an important asset that needs to be secured against access which is not allowed. Finally, the technical heart of securing some of this, if not most of the secure software supply chain, is encryption and signing. Obviously, these keys need to be very closely and tightly controlled and kept under control. After the information about security, we look into the software lifecycle. You all have seen this software lifecycle very often in DevOps environments, but it also applies to most types of software, even if the software might not be developed in a DevOps model. We have here the constant flow of planning, coding, building, testing, releasing, deploying, operating, maintaining, and then it goes back to plan. And this also applies to what we call traditional software, because also in this we have maintenance cycles, we have update cycles. So let's not focus this software cycle only to the aspect of delivering the software first time, but it is important to consider the whole life cycle, where also multiple rounds of updates, of maintenance updates, of security fixes, or even of minor improvements are due over the full lifetime and life cycle. When we look at this, the next minutes, we will consider how these 3 assets and aspects belong to each other. The information and assets, the software lifecycle, and the security aspects associated to those. Let's first look into the planning aspect. The planning aspect, or also called product configuration from a security asset perspective, is about product features. Now you might think, why is he talking about non-public information when all of this is open source? Well, it's open source, yes, but sometimes there are industry trends or industry information that as an operating system vendor we have access to that we cannot immediately share, that is under a so-called NDA. So confidentiality needs also to be guaranteed in an open source world when we are talking commercial. Obviously, from an open source community perspective, this is not the ideal case, but it's just the reality of our industry. Then we are talking about documentation of what is planned and how we are planning. There are details about product configuration and defaults. And obviously, in this planning stage, we need to control and guarantee several aspects of the security. Actually, most of those aspects are relevant. The integrity of the information is relevant. The availability of that information at any point in time, also over a long life cycle, is important. The authenticity needs to be guaranteed. Who has said that a specific product feature should be this way? And that also applies to the accountability. Decisions and certifications belong to each other. We are not only talking security certifications, but we are also discussing software certifications, hardware certifications, and it goes into stuff like a safety certification, where even the flow of information, the process of getting to these certifications is relevant to finally get it. Most of you might think about code when you think about a secure software supply chain. So in this case, the source code. Here we are talking about the origin. Is it an externally delivered software code? Is it internally delivered? For us at SUSE, very relevant, is it open source? It always needs to and should be. But in this code, we also have to consider the most two important aspects. Number one, who created it, authenticity. And number two, integrity. Is the code not changed from where it should be, where the author of the code has delivered it to us, for example, as an open source distributor? The availability aspect is something that might sometimes be forgotten when we are talking about the very fast pace of the modern software world. That's the one side. The other side is that we are discussing life cycles of 10, 15 years or even longer. And then the availability of the code, the ability to change the code kind of back in time, that is an important aspect and also contributes to the availability of the code itself. Last but not least, from a security aspect, we need reviews. And with respect to the security vulnerabilities, there is a well-known industry process called responsible disclosure, which helps us to keep the code secure on the one side, to keep the integrity, and also serve our customers with the best code at a specific time in coordination with the rest of the industry. From the source code, we go to the next step. That is building. The build aspect, and I will come to that later, is the most critical in the course of a secure software supply chain because it includes a transformation process, a transformation from source code to binary code. Here, the integrity aspect not only of the code is relevant, but also the integrity and the availability of the surroundings, of the built environment, the resilience of the production process, so that we can say, where does it come from? Who has produced it? How has it been produced? and who has testified how it has been produced. So this is very relevant because the chain of source code, which for example can be guaranteed using a Git repo with digital signatures in it, will be broken at the point of transforming from source code to binary code. I come to that later again. One aspect of at least controlling a little bit what's going on during that transformation process is what we call reproducible builds. This means that all the software transformation, the build, the compiling, is done in a way that you are removing all information about time, and you try to build the software in a way that you can reproduce, rebuild the software to exactly the same bits, given that you know exactly which tools, which environment, which source code, and which dependency source code has been available at the point of building the specific software you are talking about. This is not as easy as you might imagine, because most modern tools put some stuff of kind of time stamps into the compiled binary. And this needs to be considered when we are discussing. It also might be, for example, that you are building on a specific hardware and your compiler is executing some specific optimizations based on that hardware capabilities. And you need to be able to normalize these builds to a specific standard build, a standard hardware, so that you can later on produce reproducible builds. Again, let's move to the next topic before we come back to building again. In the test environment, we are discussing the quality criteria, which also need to have a defined origin, so authenticity. And we also need a very, very clear expectation of outcomes. The availability aspect is with respect to the availability and resilience of the testing environment, because all the testing is only then useful if you do it all the time, if it is also kind of reproducible, if you have very clear guidance and you know what you are looking for. After the test phase, you go into release. And here, I think most of you know, digital signatures play a significant role. We see that in most operating systems, in most ways of delivering software. Kind of a side note, there are some ways of distributing software these days where digital signatures are not yet there. I'm personally a little bit skeptical if this is really the best way of shipping software. All infrastructures to ship software should have at least the option to add digital signatures there. Like RPMs have it on the SUSE side. The DApp packages used by the Debian community have digital signatures. And many other package formats do have digital signatures. It is also relevant, though, to secure more than just the stuff, the entities that you are shipping. Also, the transport channel needs to be secured. So not only one single package, but if we are thinking about the Linux distribution of, let's say, 3,500 packages, you also need to make sure that the channel where this stuff is shipped really is secured following the security guidelines such as authenticity. We need to make sure that software from SUSE really comes from SUSE. On the other side, if you are creating software, let's say open source software, and someone would take this software and put it somewhere, but changing something to make your software worse, not taking about worse things, then you want to be able to refute that this software is from you. So this works in both directions, right? We want to make sure that someone can control whether the software is from the person he or she thinks on the one side. On the other side, the one who creates software also wants to be able to say, hey, this is my software, yes or no. And if it is his software, then both parties should be able to agree and prove that this really is the case. So this is why non-repudiation and accountability here both are relevant, depending from which side in the software supply chain, the supplier or the one who takes the software, you're looking at. The user of the software then deploys, and he needs to be, or she needs to be able to verify the authenticity and the integrity. This is relevant because in the end, the goal of the one who uses the software is to use that software in a compliant way. Most organizations these days have compliance needs, and thus this is the final goal when deploying and also when operating. During operating, an additional aspect, though, is added. This is the support. And the support agreement requests that you have customer agreements between supplier and buyer. And this requires that you have confidentiality about the mutual confidentiality about the information exchanged here in terms of such a support agreement and a support case, for example. Nobody wants that the information about specific support cases is published. Again, this is a matter of compliance for both parties in this context. And finally, we are discussing the maintenance. I said already before that an important aspect of maintaining software is a committed life cycle. This is relevant because we are talking about long times, 10, 15, 16 years of life cycle for a Linux enterprise operating system these days, in general, but also in specific use cases such as embedded or edge. And here the security aspects become relevant right from the beginning. We are discussing reviews, proactive work. We are discussing the ability of providing fixes for the software. And again, we need to make sure that the ability to provide responsible disclosure together with industry players remains in place. Summarizing and coming back to our cycle, secure software supply chain requires that we have end-to-end knowledge about the software and end-to-end knowledge about the processes around this software as well. However, and we can certainly say that we do not need endless knowledge about software and processes, just as a small side note. Looking at the community, there are some example initiatives I would like to mention now. And in this list of things, like the public code repository that is currently planned in Germany, or the Linux Foundation, who looks into open source software supply chain security, or the more cloud native topics like Intoto or Grapheas, I would like to have a few words about Git and later on about the Open Build service. Git as a, let's say, cousin of the Linux kernel, also originally started by Linus and the kernel team. Git is very interesting because it builds a infrastructure or a code base which is secured by digital signatures. And if we are taking this serious because it's trees, we can, with dependent check-ins and then again re-signing these check-ins, we can also use Git basically as something like a blockchain. A colleague in the security area hinted me to that. And I think this is a good way of looking at Git. If you are taking Git serious, then you can really build a very trusted chain within Git as long as you are not leaving Git. This is a very important aspect. And it also is relevant that you keep the root of trust always in your hands, and that you make sure that there is not only one instance of your Git, but that you have multiple instances so that this virtual blockchain is secured as a blockchain should be, with multiple instances which control each other. I already indicated before that building is the most critical aspect, the weakest link, so to say, because it is a transformational process. And this transformational process comes from the fact that due to compilation of larger programs, neither the result are predictable nor verifiable, because it's a transformational process, which again is done by software, and that goes to the context of complexity. In other words, we could, when we take this very seriously, say that during this process, any secure software supply chain is interrupted or broken. And this means that we have to build kind of a extra secure container confinement around the build process. We need to very tightly control the build infrastructure, the build tools like compilers, interpreters, linkers. We need to very closely control what's going into this build process and which dependencies we have. We need to very tightly control the processes and also the signing of the final deliverable. SUSE is doing this for 28 years, and we have put our knowledge about building and maintaining code into an open source project called Open Build Service. It takes input in all forms. It also allows Git integration, direct, indirect, staged, with vendoring, via tars in between, everything, but also direct integration with Git environments. And as an output, allows to produce most things you can imagine: containers, packages in RPM and deb format, VM images, ISOs for installation, cloud images certainly as well. Open Build Service is available on all architectures that SUSE looks into, from 32-bit ARM over Intel AMD, 64-bit IBM Power and Z, and also certainly ARM, but also some future architectures like RISC-V we are looking into, and also architectures that have been forgotten have been able in Open Build Service before. We also do not only build on one Linux distribution, but on multiple Linux distributions. So all the big Linux distributions are supported in the Open Build Service. All assets, sources, binaries, and signing keys are stored. It is a free and open source software that you can download, and that also goes towards really implementing reproducible builds, as we discussed before, why this is useful. We have 100 plus users, or let's say using companies worldwide, which are using the Open Build Service, and where we know from that they use it. It's developed by the OpenSUSE community and SUSE as a company. As said, it is fully open source, and it has significant benefits because, as I said, we have taken all the knowledge that we have gained over the last more than 2 decades and put it into this. It gives full visibility into how SUSE builds and maintains software, because also our OpenSUSE community is using it to building and maintaining their software. And not only enables specific processes, but it enforces processes. More or less, it's a toolified production process of a specific part of the secure software supply chain. Other processes are built upon or can be associated to it, such, for example, OpenQA. You can integrate it into CI/CD environments, and I already said Git. This gives trust, and this is why we are publishing it and why we are a little bit proud about this service that we are also offering to other communities. Let's go back. Secure software supply chain is the ability to secure, document and trace sources and binaries, build environment and update mechanisms of a specific workload over its full lifecycle, to gain trust into and keep control over machines, processes, businesses, human beings, and finally, data. Having said that, I would like to encourage you to look at your software supply chain. Please go ahead, validate what you have done, what your suppliers do, or what you as a supplier do. Enhance and enforce the end-to-end trust. I think we have seen today that it is relevant to have this end-to-end trust on the software side, on the lifecycle side, on the security side. And please also help all of us to by contributing to an open source software supply chain security. This is very relevant because open source technology becomes more and more relevant these days, and we all would like to see this grow and contribute to all parts of human life. Thank you very much.